Howdy everyone, and welcome to the tutorial video for chapters 9 and 10, where we'll look at some example problems for electron configurations, periodic trends, Lewis structures, and VSEPR. And congratulations for reaching the end of the semester. Alright, so if we look over here, oops, there we go. Now this one, I combined them in the homework. Oftentimes it'll be one type of configuration where it will just say, write the full configuration, then another problem will be write the condensed. But I thought it would be helpful to look at all three for the same elements combined, just to be able to compare and contrast, make sure we know how to do all of them. Missed some bullet points there. So we'll look at strontium and germanium. I would recommend, if you haven't already, pause the video, get a periodic table handy, because you're going to want to see where are these. So I'm going to go ahead and on my other screen here pull up a periodic table so that I can also look at it, because I've got a lot memorized but not everything, so let's just always make sure. Alright, so for strontium we go ahead and find it. It's element 38 down there in the 5th row, and so we're going to start at hydrogen and 1s and keep going till we've got those 38 electrons placed. So we start with 1s2, we then move on from there where we'll have 2s2, 2p6, that gets us through neon. We'll now go to the 3rd row where sodium and magnesium are, so that's 3s2, over to aluminum through argon, so 3p6. Now we're into the 4th row, so 4s2. Here's where the first tricky bit can happen. Remember that the d orbitals are always one number less than their row for that label. So instead of 4d, we start with 3d, it's one less. Excuse me. We fill in all 10 boxes from scandium through zinc, so 3d10. Now we're into the 4p section, so gallium through krypton, 4p6. And then, okay, there we are in the 5th row. Strontium's the 2nd box, so it's 5s2. And that's the full configuration of strontium. Right, so that's that one. If you count 2, 4, 10, 12, 18, 20, 30, 38, 32, it's up to 30, 36, 38, sorry, 38 electrons, we want them. All right, for the condensed, this is where we use the noble gas of the preceding row to go ahead and figure out, where can we start with a shortcut. So we look at strontium and say, hey, right before it was krypton at number 36. So we'll write krypton there, and then we'll go ahead and say, okay, what comes after that? Well, krypton gets us through 4p6, so it's just 5s2 after that. All right. Then for the orbital configuration, again, we're going to combine it here with the condensed so that we don't have to draw everything. We would just put krypton core, we draw a blank and label it 5s, and because there's 2 electrons, that means we'll need 2 arrows. And for the Pauli principle to keep them paired, 1 up, 1 down. So those are the 3 configuration types for strontium. So you can kind of see how we got all those. Now we're going to go ahead and get germanium, which is over there where number 32, so not quite as far. Again, we always start with 1s, and we say, yep, we fill in the hydrogen and helium, 1s2. Then we move on to 2s, where lithium and beryllium are, 2s2. Then boron through neon is 2p6. We keep going, next row, 3s. We fill in both sodium and magnesium on our way, so 3s2. Then we go to 3p, and all the way aluminum through argon, so 3p6. Now we're in 4s, 4s2 for both potassium and calcium. Again, 3d, make sure you drop that number by 1. We fill in all 10, and then we get to 4p, but don't fill it all the way up. Germanium is the 2nd element, so it's 4p2. And we stop right there. For the condensed, this time it's not krypton. We haven't made it that far. Argon is the noble gas that comes before it. So we put argon in brackets, and then that gets us to kind of the 3p6 here. So we say, what comes after that? Well, 4th row, so 4s2, 3d10, and then again 4p2. And there's our condensed. And then for the orbital, I'm actually going to draw it down here a little bit to have a little extra space. We'll put argon in brackets. For the 4s, you have 1 blank. For the 3D, because it's D, we have 5 blanks altogether. 4, 5, so we label that 3D. And for the p orbitals, we have 3 blanks. If you ever forget how many blanks do I draw, just say, well, it's 2 arrows per blank. I know if p maxes out at 6, well, 6 divided by 2, 3 blanks. D maxes out at 10, 10 divided by 2, 5 blanks. S maxes out at 2, 2 divided by 2, 1 blank. Okay, that's the 4p. Now we go ahead and label, so 4s2, so up, down. 3d10, even though we know it's going to be filled up, practice good habits with Hund's rule. We'll do up, 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 up for the first 5. Then we'll do down, 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 down for the next 5. There's our 3d10. And then for 4p2, it's up and then up. So germanium has these 2 unpaired electrons in the 4p, and that might lead to some effects as when you go into the actual reactivity of germanium. All right, so there we go. 2 examples, some with unpaired electrons and more blanks, some without. But hopefully that'll help you in the ones on the homework. All right, next up from Chapter 9 is periodic trends, where we looked at atomic size, atomic radius. We looked at ionization energy, and we looked at metallic character. And so when we looked at this one, I'm going to draw like a little cheat sheet of the periodic table. It's a little sketch that I'll draw here. Won't be perfect, but it'll be close enough. All right. And then, we said that the largest, we're down here in the bottom left because things get larger as you go top to bottom. They're also larger on the left-hand side. The things shrink as you go right. So now we're going to say, let's find these elements on the periodic table and put them in order of smallest will be in the top right, largest will be in the bottom left. So fluorine is right about there. Let's see, sulfur is right about there. Silicon is a little bit over from that in the same row. Let's see, where's the other one? Calcium is right here. Rubidium is right here, below it and to the left. Which one am I missing? Oh, germanium. Germanium's right under silicon in the same row as calcium. So I think that's all 6. Yep. So if I look at that, for all these, I'm going to say the smallest one will be in the top right. Well, that's fluorine. But let me here put smallest, so we know which way we're going. Let's see, and then we just start moving to the bottom left. So sulfur comes next. To the left is silicon. And then below that is germanium. And then we keep going left, 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 and there's calcium. And then down to the left of that is rubidium. So that would be the largest of these 6. So that's really all you're doing when you have a question on atomic radius. You say, okay, let me remember where the largest ones are, and then just go for the opposite corner and work your way that way. Okay. Sometimes you get problems that are comparing 2 elements, and if they're ever like here and then maybe down here to the right, then you say, well, I don't know, because it's down, which is bigger, but to the right, which is smaller. That's where you might have not enough information. But whenever you're given a series like this where there's a whole bunch of elements, they're always going to follow a pattern. There won't be any ambiguity or, well, I don't know about this one. Just, no. Top right, bottom left. All right. Next up is number 55, drawing Lewis structures. I will encourage you, if you're having trouble or just confusion about how to draw them on the Mastering Chemistry homework program, remember there is that Introduction to Mastering Chemistry assignment, which is not an assignment. It's not worth any points. That's just the how do I do problems on Mastering Chemistry. They have one specifically in there about drawing Lewis structures. And so I encourage you to go there to say, not that, I got the right structure on paper. I know how to do it on paper. How do I get it on the computer? Go to that Introduction to Mastering Chemistry. Practice the one there to make sure you say, okay, now I see how I connect them with bonds. How do I put in the lone pairs? How do I do that stuff? Because then that way you'll be pretty good there without wasting an attempt on your actual question. All right, but for these, we'll just draw them on paper. So we have selenium dioxide and carbonate ion. So step 1, we put the central atom the first atom in the middle, other atoms connected by single bonds. Step 2, we give the outer atoms an octet. So we go ahead, don't know what that was. Hit a little wheel on the tablet here. Third step, we're going to count. All 3 of these elements, again, have your periodic table out. All of them are 6A. So 6 plus another 6. I'm supposed to have 18 electrons total. Currently drawn, we have 16 electrons drawn. And so when we subtract that, we got 2 electrons that are missing and still need to be added. Step 4 says add any missing electrons to the central atom in pairs. So we'll go ahead and add those 2 dots on the selenium. And then step 5, check to see if the central atom still needs an octet. If so, move electrons to make a double bond until you get to 8. So the selenium has 2, 4, 6. So yeah, it still needs an octet. I'm going to take maybe these 2 electrons and move them over. So let me get the eraser. And we'll just say, okay, yep, get rid of those 2. Swing them around and make a double bond there. Now the selenium's got 2, 4, 6, 8. This oxygen still has 2, 4, 6, 8. There's still 18 total, so that is the finished structure there. Now for carbonate, this one's a polyatomic ion, so we got to remember when we're counting electrons, we got to add in this case, 2 electrons to get that -2 charge. So just don't forget about that. We put the carbon in the middle. We'll spread out our 3 oxygen atoms. Step 1, we'll go ahead for step 2, give all the oxygens the 6 dots to complete their octet. Step 3 is where we count. So we say, okay, carbon is under 4A, oxygen's under 6A. So that's 4 plus 18 is 22. But here's where we say, okay, let me put it over here. 4 plus 18. But to get a -2 charge, we have to add 2 electrons there. So that's 24 electrons total. We look and draw, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have the 24 drawn, which means, yeah, we're not missing any, so no dots to draw. So skip step 4, but step 5, does the central atom have an octet? And we say 2, 4, 6. No, it doesn't. It does need one. So again, we're going to move some electrons and make a double bond. So again, we'll erase those 2 and swing them around and make a double bond there. The last thing is, if you're doing this on paper, or anyway, you just put them in brackets to say that this is the ion. Don't forget to put that charge in the top right corner so that people know that this is actually carbonate with the -2 charge and not some weird carbon trioxide that doesn't exist. All right, last question then is 65 and 67 together. I actually put the corresponding questions together on the homework, where you're going to do the 66 in that case first. The same molecules will be used in the next problem, so make sure you have the first one right. Whether you use all your attempts to get the right answer or not, just get the first one right, because then you'll use that answer to get the second part. So the first part is get the molecular geometry, the molecular shape, and the second part is, once you know that shape, what's the bond angle? So we'll do this one first, carbon tetrabromide. But the first step is still draw Lewis structures. So you draw your 4 Lewis structures. Step 2, give them an octet. Okay. If you count this up, carbon brings 4. Each bromine brings 7, so that's 28, and 4, that's 32. We have 32, so there's no more dots to draw. We check the carbon. It has an octet, 2, 4, 6, 8. So that one's done. And so what we look at then for molecular geometry, we say that there's 4 electron domains 4 regions of electron density, that means it's a tetrahedral electron geometry. And then from that, we say, well, all 4 of them are bonds, so then the shape is still tetrahedral. The name doesn't change when everything's a bond. So that's that one. So that's the molecular geometry. And then if you were to go on to the next problem, you say, oh, what's the bond angle of that? Well, you just look it up from the table, make sure you know these numbers. For tetrahedral, it's always 109.5 degrees. So there's the 2 answers for that problem, tetrahedral, and then that means 109.5. All right, in part B here, we're doing, this is formaldehyde actually, and they mentioned that carbon is central. So sometimes this will happen when there's more than just 2 types of atoms, or if there's H's in front, they'll just mention, hey, this atom is the central atom. That means everything's going to be connected to that. So carbon goes in the middle. I've got an oxygen, and I'll have 2 hydrogens. All right, so that's step 1. Step 2 is give the outer atoms an octet. We give the 6 dots to oxygen, which is really angular there. Oh well. But not to H. Hydrogen never gets extra dots, so we're good there. Now when we count, hydrogen is 1 each from 1A. Carbon is under 4. Oxygen's under 6. So that would be 12 electrons total. When we draw, we say 2, 4, 6, 8, 10, 12. We've got 12 electrons, so nothing's missing. But then, hey, that carbon does not have an octet, so we've got to go ahead and erase a non-bonding pair and move it to make a double bond. So we'll put it there, and then that's the correct structure. Everything has an octet that needs it. The hydrogen's got the 2 that they need, and that's the 12 electrons total. So there's our picture. We now then say, okay, the molecular geometry. We look at that carbon, and we say that there are 3 domains, which leads us to the trigonal planar shape. All 3 are bonding, which means the molecular shape is still trigonal planar. Right? When all the domains are bonds, the names are the same, so that happened for both here. So that's that answer. What's the molecular shape? Trigonal planar. And then what's the angle? When we look at that, when 3 things spread out equally, it'll be about 120 degrees. All right, so that's how you do those problems. So that's actually 2 separate problems on the homework, or that you commonly get, but you have to do the whole process every time. And so that's even going to come up on the exam, where it'll be a multiple choice problem, but it'll say which one of these has angles of 109.5. Well, what that's asking you is which one of these is the tetrahedral electron geometry. So you got to draw your Lewis structure first to be able to figure that out. So the whole process is very important to be able to get the whole thing. That's the end of this video. Again, if you need help, office hours, email, tutoring center, ask for help, please. It's the end of the semester. We want to finish strong, and we want to get you the help you need. So with that, have a wonderful day, and good luck on your upcoming exams.